equal to 4 pi r squared, where r is that length, so from the centre to the edge. Alright, so imagine that we have a star, and at some distance away there's a person. There you are, d away. Now the other thing that as physicists we really like to do is we like to write everything as symbols, but they're not intimidating. You can substitute them for a number if you would like. So the actual answer is a quarter.
Okay.
So it's a half squared, which is a quarter. The reason for that is we go back to the equation for the day, 4 pi r squared. So when you think about how light spreads from a star, right, you can think of the light as it starts off as essentially a point, so the star, and then the light goes in every direction, right? So the light goes out from the star in every direction, just like that. So if you have someone looking, put some nice eyelashes on, and at a distance of 1 meter, there's a stick, and that's also 1 meter high, right? Now, just think about the sort of angle that covers. Now, if that same 1 meter stick doesn't help, we're 2 meters away, right? There's another 1 meter stick. Then, if you were to draw a line back, you can see it sort of covers about half of the original angle, and it actually intersects the original 1 meter line at a half, right? That the universe cannot be infinitely old, infinitely large, and have infinitely many stars at the same time. Why is this? And all you need are the 2 things we've learned today.
So these 2?
Yes.
And this one as well, I guess?
Yeah, I mean, that was used to derive one of those, but so you don't actually need that. Alright, feel free to take a seat.
Thank you.
Do you want some tea or coffee? You prefer tea, I know.
Yeah,
I have some
if you have any.
green tea.
Oh yeah, thank you. That looks lovely. Thank you.
Nice. Sorry, I don't usually make tea.
Oh, do you usually have coffee?
Yeah. I got this as like a gift.
Oh, okay.
So it's probably fancy. It's probably nice.
Yeah, it looks.
Probably in date.
Thank you.
Yes.
Oh, it smells lovely.
Okay, let's get started.
Thank you.
Cheers.
Cheers. Well, thank you for having me.
Thank you for coming. I guess today we want to talk a little bit about physics.
Yeah.
The last time you did physics was at GCSEs, right? So that's 16 years old?
Yeah, back when I was 16, so...
It's been a while then. In contrast, just to sort of introduce myself, I do a physics PhD here now at Cambridge. I mean, obviously you know, but this is more for, I guess, the camera.
Yeah.
And today I thought it would be sort of nice to do a little lesson, I guess, that I did for an outreach course to some GCSE students. I'm just going to get my iPad so I can look at my notes from when I did it. And it's going to be about how equations are your friends. Because I think the image you get from maths and physics at school is that equations are your enemy. They're the things that, that can lose you marks. They're not fun, but I'm going to try and convince you today that equations are really the way to think about the world. They're a great way. They're the tool that physics uses to model the physical world around us. And hopefully you'll find it a little bit fun along the way.
Thank you. I'm excited.
Well, we'll see how it goes. So, the first little question I have for you, and we're going to try and do this in the sort of form that I'm most used to. So in Cambridge we have these things called supervisions, and I mean you'll obviously know, but they're like these one-to-ones with academics that you have every week, and you usually do some homework before you go in. Now, I wasn't so cruel as to set you a grown person with real homework, so today we'll instead be going through the questions on the spot. So yeah, let's get a sheet of paper out.
Thank you.
There's also a calculator if we need one. I don't think we should need one.
It's been a while since I've seen a calculator.
So the first question is, do you remember the surface area of a sphere?
2 pi r.
2 pi r is the circumference of a circle. So if you have a circle like that with a radius of r, then the circumference, so the length of, as you draw around that, is equal to 2 pi r. So what we're instead thinking about is a sphere, right? Which looks quite similar to a circle, but it's actually 3D, so it's like a globe. So when you think about the surface area of that, so that's that's the area that the surface covers. So if you were to peel it like an orange and lay it out flat, what area would it occupy? And that is equal to 4 pi r squared, where r is that length, so from the centre to the edge, and the pi is pi. Hopefully you've heard of that. It's 3.14. It's just a constant, 3.14, and it keeps going on. But I don't know any of the digits beyond that, and I don't think anyone really needs to know anymore. So yeah, let's keep this in mind. Let's keep this off to the side so you can see it.
Thank you.
The nice thing is this is the only equation you'll need today.
Oh, that's great.
Because the whole point is equations are your friend.
It's one of the few I vaguely remember from school. This and like Pythagoras and stuff.
Oh yeah, a squared plus b squared is equal to c squared.
Yeah. But yeah, I haven't used them in my life since, so.
Yeah, it's interesting because I think you learn all these things at school and then it's like, oh, when will I ever use them? And I think it really depends on the person, right? Because I obviously use Pythagoras a lot. I use sines and cosines a lot. I use that a lot.
Yeah.
And to me, it's like, yeah, of course you'll use them. They're sort of fundamental. But I can understand that some jobs you don't really need that. Alright, so imagine that we have a star. And at some distance away, there's a person. There you are, some distance d away. Now, the other thing that as physicists we really like to do is we like to write everything as symbols. But they're not intimidating. You can substitute them for a number if you would like. So there's person A, and then another distance d away, there's person B. So person B is essentially twice as far away from this star as person A is. So if person A perceives the star to be some brightness, I'm going to give it another symbol, B. Love symbols, actually. B is a bad symbol because I just called that person B. Let's call the brightness beta. How bright will the star look for person B? I think.
Gosh, maybe it will look like half as bright.
Okay, that's a decent idea to go for because you're twice as far away, so maybe it looks half as bright. That's actually wrong though.
Oh no!
But it's a good first guess, I would say. So the actual answer is a quarter.
Okay.
So it's a half squared, which is a quarter. The reason for that is we go back to our the equation for the day, 4 pi r squared. So when you think about how light spreads from a star, right, you can think of the light as it starts off as essentially a point, so the star, and then the light goes in every direction, right? So the light goes out from the star in every direction, just like that. So if you were to think about this in 3D, all of these together, they form a sphere around the star, right? So it's like, if you were to like turn the light bulb on and off just for a split second, you can imagine that there's this shell of brightness around the light bulb that emanates out into space. Does that sort of make sense to you?
Yeah.
So there's this sphere. So even if the light bulb is continuously on, there are these spheres of light that were each emanated at a particular point in time, and there's just an infinite number of these spheres. The brightness that you'll perceive is, so if you think of these spheres going out into space, they're like balloons inflating, then you can imagine that the density of the light on that surface is going to be slowly diluted by the surface area of that sphere, right? So you go from a little circle where all of the light is on that, and the light isn't lost, none of the light goes, it just keeps on emanating out. It doesn't just disappear into the ether. It so to say, it actually does preserve. It is preserved, but it's just spread out and spread out and spread out, so it looks less bright as you go far away. And the way that it looks less far away is because it's spread out by this surface area that we said, 4 pi r squared. It is to 1 over that area, because it's the density of the light almost, so it's dividing by that surface area. So you end up with that the brightness at some point is going to be correlated with 1 over that sort of surface area. So because of that, if you're twice as far away, it's going to be 1 over 2 squared, so a quarter of the brightness. Does that make sense?
Yeah. I think so. I'm trying to get my head around it. But
yeah, it's a different way of visualizing light, right? You think of these light rays, I think that's the one that you've thought about, but if you think about a star or a light bulb, the light actually goes in every direction, so there's an infinite number of those light rays in every direction.
Yeah.
Maybe that's a good way to think about it.
Yeah, that's a really helpful way of thinking about it.
Okay. Actually, the next one might even you can think of it with Pythagoras, I guess. So the next one is if we go back to this.
Okay.
The star's not actually like this pointed shape, right? It's like a little circle. But how big does the star look for person B compared to person A?
Gosh. So person A was a quarter.
Well, the person A is half the distance away, but now if they're...
Do you know what just double is? Or is that really dumb?
Well, no, again, that's a decent idea to have, right?
Yeah.
So you think that the star looks twice as big for person A as it does for person B?
Yeah.
Yeah?
It's going to seem twice as small to B than it is to A.
Yeah, but what do you mean by small? When you talk about how big something is, you can either talk about its area or its diameter, or, right? Like if you look at someone from twice as far away, when you say they're twice as big or twice as small, is it like they're half the height? Is that what you're saying?
Oh gosh.
Or is it that the area that they cover is half the amount? Right? Because they're slightly different things.
Yes, they are. And I have absolutely no idea.
Right, let's think about it. So if we have, and I'm going to use very simple numbers here to try and make things a little bit easier. So if we have so if we have someone looking, draw some nice eyelashes on, and at a distance of 1 meter, there's a stick, and that's also 1 meter high. Right? Now, just think about the sort of angle that covers. Now, if that same 1 meter stick doesn't help, we're 2 meters away, right? There's another 1 meter stick. Then, if you were to draw a line back, you can see it sort of covers about half of the original angle, and it actually intersects the original 1 meter line at a half, over half, right? So that means that as you get twice as far, the height, or you can also imagine this to be a circle a meter away, so in this case the diameter gets half as much, or the perceived diameter, if you didn't know the distance, gets half as much. What that means though is that the area covered by one of these circles also becomes a quarter, right? Because the area is equal to pi r squared, so the area you see becomes a quarter. So that's what I was trying to drill in when I said, well, what's the sort of, what do you mean by smaller? Because you are right in that it looks half as small.
Yeah.
But you have to say the height or the diameter or the radius looks half as small, whereas the area looks a quarter as small. So I was just trying to get that distinction in.
Yeah. Okay.
Does that make sense?
Yeah. I think the drawings really help. Like, I was never the best at this sort of stuff at school, but I think you explain it really well, and
thank you.
The drawings are really helping me visualise it.
Now, from these two answers, we can actually answer a very interesting, in my opinion, a very interesting paradox, and it's called Olbers' paradox.
I mean, I've never really heard of any of these theories, because I guess with GCSE level you don't really...
Yeah, I think all the components to do this you have at GCSE, but it's just about showing that that equation is not just for your GCSE maths exam. It's something that is actually usable.
It sounds really basic, but it's actually quite fascinating for me in that. But back when I was doing these subjects at school, maths and physics, to an extent, they were separate things in my mind.
Yeah.
And it's really interesting seeing the maths being more applied here and how they're kind of really strongly linked together.
Yeah.
And yeah, I'm sure for some other people as well, like who never did anything beyond GCSE, it's quite interesting to see all of this linking.
It'd be great. I think maths is sort of the language of physics, because you can wave your hands and make anything sound right. For example, the Greeks thought that there was this thing called impetus, the ancient Greeks. The idea of impetus was that, first, before we get to impetus, as I understand it, in ancient Greece there was this idea of things return to where they should be. Okay. So air goes up, fire goes up, because that is where they come from, the heavens, and earth goes down, and some things are in between, but and I think water goes down as well. So the sort of the 4 elements in Avatar they had, and each of those had a tendency to go up or go down. They go towards where they naturally belong, either the heavens or the earth. And there was this idea of impetus. So this was how they explained how you could throw things despite everything wanting to go somewhere. So the idea was that when you tried to throw a rock or a pen, you imparted upon it this property called impetus, and that was like their analogue of what we would call momentum. But the idea was you gave something this property and it would go in a straight line as long as it had that property, and that property then runs out and then it goes to where it would like to be. So if you were to throw, I don't know, if you were able to throw pure fire, for example, it would go in a straight line and then it would then float up. Or if you throw a rock, then you throw it, it goes in a straight line, it gets tired, its impetus is used up and it falls down. Now, if you were ever to look outside, you'd know that a rock goes like that, right? It goes in a parabola, it goes in a smooth line. But if you decide to stay inside and just talk about it, and you don't make predictions, you can make anything sound right. And that's, I think, the value of maths, because it gives you predictable, testable predictions that mean that you can say this theory agrees with reality, this theory doesn't agree with reality. Now, you can have theories that are like very, very complex and agree with reality but aren't necessarily right, or you can have theories that agree with reality to a certain degree. So that would be, so like Newton discovered these laws for gravity, Einstein discovered more accurate laws of gravity, but Newton's laws are basically enough to get us to the moon. I think the computers on the Apollo did not take into account Einstein's corrections, but that doesn't mean that. So it's like things can be a better or worse model. But anyway, the point I wanted to make was that maths is very important because it tells us how wrong something is, and whether something's wrong, and it lets us test theories and try and progress science towards having a better model of the world.
Yeah.
But yeah, anyway, back to Olbers' paradox. So, Olbers' paradox is, the question that I want to ask, which leads us on to it, is, we can deduce by looking at the night sky that the universe cannot be infinitely old, infinitely large, and have infinitely many stars at the same time. Why is this? And all you need are the two things we've learned today.
So these two?
Yes.
And this one as well, I guess?
Yeah, I mean, that was used to derive one of those, but so you don't actually even need that.
Gosh, it feels like my final question on the exam.
There we still have a few more.
Oh, okay. I have to get my blue pen out.
Yeah, if you want a fresh sheet of paper? If you want some thinking space. So, yeah. Something that might help if you're a little bit stuck is to think about the implications of these things. So if it were infinitely old, what would happen? If it were infinitely large, what would happen? If there were infinitely many stars, what would happen?
Is it to do with something about how, like, you know, when we see stars, they say, like, they're already done with their stuff, you know?
That's the implication of infinitely old. So
Yeah.
What the thing that you've talked about is that light takes some time to reach us, right?
Yes.
We've heard about there being a speed of light. So I think the moon, I'm not going to say any numbers because I know I'll be wrong. But yeah, so if the universe is infinitely old, what that means is however far away a star may be in the night sky, the light from that star will have reached us.
Yes.
By now, right? That's what infinitely old tells us.
Okay, so I'm onto something.
Yeah, you're onto something. So that's the implication of infinitely old.
Okay. And the other one was infinitely wide.
So there's two more. There's infinitely large. I mean, width and height don't.
Okay.
It could be infinitely wide. And infinitely many stars.
Well, if there were infinitely many stars, there'd be no black, like around all of them. It would just be like brightness out there.
So that is actually the answer to Olbers' paradox.
Pun intended.
But we can prove it mathematically. But that the answer to this is that it's because the night sky is dark. That is the answer.
You mean I got it?
You did get it. See, physics is fun.
I didn't even draw anything.
Yeah. I'll get around to the drawing if you want.
Sorry.
That's alright. So, yeah, so what we know,
Thank you.
let's try and formalise this, right?
Okay.
Infinitely old means that infinitely far away stars, light from infinitely far away stars will have reached us. And the other two conditions, infinitely large and infinitely many stars. This means that with whatever direction you point in, there should be a star.
Yes.
So right, it might be very, very far away, but if you point in a certain direction in the sky, there should be a star. Because if it were infinitely large and there are infinitely many stars, even though that star might be infinitely far away, whatever direction you point in, there should be something. Because we're saying that if it's infinitely large, there's like infinitely many chances for you to find a star along that path. And you're saying there's infinitely many stars, so it's not like that chance is bounded. There's. It's not like, oh, we've already used up all the stars, so we can't place a star in that direction. There's always one more star that you can add, and it's still fine. Something to note is that this says nothing about the density. So infinitely many stars doesn't mean that there's going to be like 10 stars in our solar system. The density of stars can be the same as what we have in the real world, and this can still hold, right? Now, the mathematical reason why this would lead to an infinitely bright sky is that, remember that if you're twice as far away, the light from a star is a quarter as bright.
Yes.
And if you're twice as far away, it's also a quarter of the size.
Mm-hmm.
What that means is that when you actually see the star, because it's a quarter as bright, but it's also a quarter the size, the star will appear the same brightness. It will just appear as a smaller and smaller and smaller speck in the night sky.
Mm-hmm.
But because we said that there can be infinitely, whatever direction you point in, there'll be a star. Whatever direction you point in, there'll be like this tiny speck of a star wherever it is in the night sky.
Mm-hmm.
And because it's infinitely old, however far away it is, the light from that star will have reached us, so we'll definitely be able to see it. And these relations say that because of the way these stars, the brightness and the size relates, you'll always have a star of the right brightness in the right area. So the entire night sky will be the same. It will be entirely bright. So that's Olbers paradox. And like the thing is, like, you can, as you got to it, like through intuition, say like, oh, if these things hold, then the night sky would be infinitely bright.
Yeah.
Well, not infinitely bright. Sorry, uniformly bright.
Mm.
But you can't say it in a way that people won't be able to refute without the maths, right? Whereas if you have the maths, you can say, well, because of this, like, there'll be things with this brightness, and there'll be this size, so, even though they're a quarter as bright, there'll be 4 times as many stars in that area because they'll be smaller, and like, so the perceived brightness will be, like, you can make that argument because you have the maths.
Yeah.
So I think it's really cool that with this very simple GCSE level maths, you have this implication for, well, now I know something about the universe. I don't know which of these things is false, but we know something about the universe, and we haven't left our chairs. We just looked outside at the night sky.
Yeah.
Which I think is pretty awesome.
Yeah, it is.
Okay, so the next section, we have 3 more questions. They're a little bit shorter, hopefully. So in the next section, we're going to be looking at equations, and they don't just work for light and predicting some interesting things about the universe. They actually can be used for all of physics, from electric to gravitational fields, which they're all governed by that same equation. So let's think about electric fields first. Do you remember what an electron is?
Vaguely. I remember there's like protons and neutrons and like atoms, right? Yeah.
So they're the so the protons, electrons, and neutrons are the building blocks of the atom, and there are things smaller than them, but like in principle they are like some of the building blocks of atoms, and atoms make everything. So they're in the middle of an atom. There's the protons and the neutrons. They're quite big and heavy, and then the electrons sort of whiz around them, which is. So you've probably seen the sort of diagram where it's like protons, and this is the nucleus, which has a positive charge because it's got the protons and the neutrons in it, and then there's the electrons whizzing around it.
Yes, yeah.
It's not entirely accurate. Any physicists watching this will know what I mean, but that will serve us fine for today.
Okay.
And those little things whizzing around electrons are the smallest things with a negative charge. Now, I'd like you to draw for me the electric field around an electron.
An electron.
Yeah.
Right. I'll try my best. I feel like you've given me a hint because I vaguely remember. It's like a circle with a minus. Right?
Yeah, so that's what an electron looks like. So that's a good start.
But as for the things around it, I remember there's like liney things, but I honestly don't remember how to draw them.
Well, a good thing to think about when you do these things is the symmetry, and an electron, that there's nothing special about any direction, right? It's just a blob.
Yeah.
So the field must look the same in every direction, right?
Yeah.
So that it must be symmetrical in every way, which means that the field must look something like this. The direction of the arrows is something that is sort of arbitrary, actually, but I'm going to draw them the conventional way. So, yeah, you can sort of get there just by thinking about the symmetry, right? So the electric field is going to be constantly pulling in towards the electron. Now, looking at that diagram, how do you think that the electric field from an electron will change as you go further away from the electron? How do you think the strength of the electric field will change?
The strength of it?
Yeah.
Will it not be stronger the closer you are to it?
But how is it going to be stronger, right? So we're trying to think of a mathematical equation for this, in the same way that we did for light.
Yeah.
So let's just pull up this diagram. So this was when we were thinking about light. So just remember, do you remember this diagram?
Yes.
So that was with light, right? So when you have a star in the middle and you have all the light going out.
Yeah.
Doesn't that look quite similar?
They do. Except the arrows are the other way around.
It doesn't really matter. The directions can actually, you can, if you so wish, you can define it to be the other way around. It's just convention, really.
Okay. They do look similar. Okay.
They do look similar, right? And how did light behave?
It was constantly emitting in all directions.
Yeah. And what did that tell us in terms of the equations? So if you were twice as far away, the brightness got...
Quarter.
Yep. It was a quarter. So if they look the same, why do you think they'll be different here?
So the same?
Yeah. So it behaves
It's on like a completely different scale?
Well, yeah. So even though they're very different physical systems, they behave in the same way.
That's so cool.
So the electric field will decrease with the inverse square. So 1 over the distance squared. So if you're twice as far away, it's a quarter of the strength.
Ah.
And that's because they both work the same way, right? It's about how many field lines are there at a certain place, if you think about like in that sort of diagram, and they're emitted in a spherically symmetrical way. So it's the same as light. And so you can use the same reasoning where you think about, oh, there's a sphere around it, and you're thinking about the density of the lines, and that takes you to the strength of the field is a quarter when you get twice as far.
Okay. Yeah.
Isn't that cool?
That is cool.
And you don't need to do much in the way of experiments or thinking to get there. You can sort of like reason your way to it from like looking at that, oh, it's spherically symmetric and the strength is proportional to the number of field lines, and you can get there the same way you did for light, which I think is quite remarkable, and you get an actually testable mathematical sort of theory out of it, right? Now, the final one is we have the Earth. Imagine we have we do have the Earth, but imagine the Earth. Let's draw. I'm gonna. It's gonna be terrible because I've probably missed out a lot of countries. I was about to miss out the UK, and there's you on the surface of the Earth, somewhere in the middle of Asia for some reason, because that's how I drew it. So there you are, in the middle of Asia, and at that point you're about 6,371 kilometers from the center of the Earth. I don't know this number off by heart, by the way. Neither should you. It's not a particularly useful number. Now, the force of gravity at that point is 9.81 meters per second squared. You don't need to know that number that well either. It's just a number so that we can actually do the calculations.
Okay.
Now, imagine you're an astronaut, and you are at a point 12,741 kilometers away from the Earth. So you're out here, on some space station. Is that what space stations look like? I don't know. But you're out there like orbiting the Earth. But if you were to just like be stood, let's not think about the space station actually. But if you were out here and you were just stuck in space, like out there, and you were stationary, what is the force of gravity that you feel there?
In space?
Yeah, at that distance. Not space in general, but that distance in particular.
I've got absolutely no clue.
Well,
I know, like, it's different. Oh, I'm going to sound really dumb no matter what I say. Like, I know gravity's different in space.
well, it's not different in space.
Okay.
The way gravity works is just the same as the things you've looked at. There's a central mass, and then there's a gravitational field pulling things towards it.
Mm-hmm. Oh, it's the same thing again?
Yes.
Ah.
And because this distance is conveniently twice the circumference, the gravitational acceleration would be, so the force of gravity at that point would be
Do I do right? Second squared or?
meters per second squared. So yeah, all of these things behave in the same way, whether it's light or the electric field or the gravitational field around the Earth. All of these behave in the same way, where you can reason that out just by thinking about the sphere around things. And the reason why I started to draw the space station orbiting, and then I was like, I erased the arrow, by the way, is because you know how you said in space gravity's different?
Yeah.
There is some reasoning behind that sort of intuition, and that's so space stations actually fly like around here, like very close to the surface of the Earth. They don't fly that far away.
Okay.
But whenever you look at so if you think about this sort of relation, the gravity there is about the same, essentially.
Yeah.
Because it's still very close to the surface of the Earth, right? But the astronauts up there look very weightless and floaty, right?
Mm.
The reason for that is because when you're in orbit around the Earth, it's like the way it works is like you know when you're on a roller coaster and you go down and you feel weightless for a second.
Yeah.
The way space station orbits work is that you're constantly falling.
Okay.
So that's why they're weightless.
That's cool.
So when you're orbiting the Earth, you're weightless not because gravity doesn't exist there.
Yeah.
It's because you're constantly moving and orbiting around the Earth. But because you didn't.
Yeah.
That was an aside. That doesn't actually.
But it's still
answer
interesting.
this question.
Ah.
But yeah, hopefully I've shown you a little bit that maths is, well, for one, useful.
Yeah.
It's the language of physics, and the great thing is it's applicable to many things. If you use it for light, you can use it for electric fields, and you can use it for gravitational fields.
Yeah. No, I'm glad that I came today. Thank you. It was really insightful. Like, I think it's taken away a bit of the scariness I have associated with these sort of things. I think having not touched this sort of stuff in a long time, it made me a bit scared to come back to it. But no, it's really interesting, and the diagrams really helped.
That's good.
So thank you for your time, and yeah, very insightful. Thank you so much.
Thank you.